Summer 1940. Britain stood alone against the Nazi war machine, and the Luftwaffe controlled the skies. Every Spitfire, every Hurricane depended on one thing: the Rolls-Royce Merlin engine. But British factories couldn't produce them fast enough. Desperate, Churchill turned to America. Packard Motor Company agreed to build Merlins under license, with one condition from Rolls-Royce engineers: don't change a single blueprint, not one bolt. The Americans smiled politely. Then they did exactly what they were told not to do. What happened next would save the war. September 1940. The conference room at Packard's Detroit headquarters smelled of machine oil and tension. Sunlight filtered through factory windows overlooking production lines that had built luxury automobiles just months earlier. Now those lines stood silent, waiting for transformation. At the head of the mahogany table sat Colonel Jesse Vincent, Packard's chief engineer, a man whose grey eyes had seen every mechanical challenge the 20th century could offer. Beside him, 3 British engineers from Rolls-Royce sat rigid in their wool suits, uncomfortable in the Michigan heat, clutching leather portfolios containing the most valuable secret in the Allied arsenal. The Rolls-Royce Merlin V12 engine was a masterpiece of British engineering. 1,030 horsepower of precision machinery that turned Spitfires and Hurricanes into the defenders of civilization. Every component was hand-fitted by craftsmen whose families had worked metal for generations. Each engine took 6,000 man-hours to complete. Britain needed 30,000 engines. Their factories, working maximum capacity under nightly bombardment, could produce 200 monthly. The mathematics were brutal. At current rates, Britain would lose the war before enough engines could be built. The senior Rolls-Royce representative, a man named Hives, with a clipped accent that suggested Cambridge and generations of engineering tradition, opened his portfolio with ceremonial precision. "Gentlemen, these blueprints represent 15 years of development. Every tolerance, every specification has been proven in combat. The Merlin is not merely an engine, it is the reason Britain still fights." He paused, fixing Vincent with a stare that had intimidated junior engineers across the empire. "You will manufacture these engines exactly as drawn. No modifications, no American improvements, no clever ideas. We've specified imperial measurements, British standard Whitworth threads, tolerances achievable only through skilled hand-fitting. Any deviation compromises the engine's integrity." Vincent studied the blueprints spread across the table. His team, experienced engineers who designed everything from luxury car transmissions to marine engines, leaned forward, their expressions shifting from curiosity to disbelief. The drawings were immaculate, rendered with the precision of men who viewed engineering as art, but they were also impossible. Every dimension was in imperial fractions, 64ths of inches, thousandths that assumed craftsmen would hand-file components to perfection. Thread specifications called for Whitworth standards that American manufacturers had abandoned decades earlier. Tolerances required individual fitting, hand-lapping, adjustments made by men whose fingers could detect variations invisible to instruments. James Robertson, Packard's production chief, a Scotsman who'd immigrated to Detroit 20 years earlier, spoke carefully. "Mr. Hives, these specifications assume manufacturing methods that don't exist in American factories. We use decimal measurements, standardized tooling, interchangeable parts. Our workforce comes from mass production lines, not craft apprenticeships. We'd need to retool every machine, retrain every worker, import specialized materials. It would take 18 months just to prepare." "Then you have 18 months, Hives replied coldly. "Britain doesn't have the luxury of American efficiency. We need Merlin engines built to Merlin standards. If that's beyond Packard's capabilities, we'll find another manufacturer." The room fell silent. Through the windows, Detroit's industrial landscape stretched endlessly. Factories, foundries, the greatest concentration of manufacturing expertise the world had ever known. America could build 50,000 aircraft annually, 100,000 tanks, entire fleets from raw ore to finished steel in months. But Britain was asking them to abandon everything that made American manufacturing powerful: standardization, mass production, interchangeable components. They were being asked to become British craftsmen in American factories. That night, after the Rolls-Royce team departed for their hotel, Vincent gathered his senior engineers in the quiet factory. The overhead lights cast harsh shadows across their faces. "Gentlemen," he said quietly, "we're going to build the Merlin engine, but we're not going to build it their way." The engineers exchanged glances. What Vincent was proposing bordered on insubordination, redesigning an engine that powered Britain's survival without British permission. "We'll convert every dimension to decimal," Vincent continued. "We'll replace Whitworth threads with SAE standards. We'll redesign components for machine production instead of hand fitting. We'll engineer tolerances, achievable through American tooling. And we'll do it in 6 months, not 18. He paused, meeting each man's eyes. "The British are dying while their factories can't produce enough engines. We can save them, but only if we do it our way." The risks were enormous. If the redesigned engines failed, Britain would lose faith in American manufacturing. Pilots would die. The alliance would fracture. But if they succeeded, if they could prove that American mass production could match British craftsmanship, they would demonstrate something profound: that democracy's greatest weapon wasn't individual brilliance, but collective industrial might. October 1940 through February 1941. The Packard engineering department became a fortress of focused desperation. Every night, after the Rolls-Royce liaisons departed, still insisting on exact blueprint compliance, Vincent's team returned to work. The factory's second floor, normally used for prototype development, was converted into a secret redesign laboratory. Guards were posted. Only engineers with specific clearance could enter. Inside, under bare incandescent bulbs, 30 men worked shifts around the clock, systematically translating 15 years of British engineering into American manufacturing language. The challenges were immediate and brutal. The Merlin's crankshaft, a masterpiece of forged steel that required 60 hours of hand polishing, needed to be redesigned for automated grinding. Every bearing surface, every oil passage, every dimensional relationship had to be recalculated. British specifications called for 0.0015-inch tolerances, achieved through craftsman intuition. American machines needed explicit dimensions that workers could measure with micrometers. The connecting rods, hand-selected for weight matching within 2 grams, required statistical analysis to determine acceptable mass variations for automated production. Thomas Archer, the metallurgist, faced perhaps the worst challenge. British aluminum alloys were proprietary, their exact compositions unknown. Rolls-Royce specified RR56 aluminum with no further detail, assuming manufacturers would source it from approved British suppliers. But American aluminum came from Reynolds and Alcoa, with different purity standards, different trace elements, different crystalline structures when cast. Archer spent weeks testing combinations, measuring tensile strength, heat tolerance, fatigue resistance. His laboratory became a museum of failed pistons, components that looked identical but cracked under thermal stress, warped under compression, failed after 20 hours when they needed to survive 400. The machine shop worked parallel miracles. Every component required new tooling. Crankshaft grinders needed modified wheels. Cylinder boring machines required precise jigs that didn't exist. The supercharger, a complex spiral of impellers and housings that forced air into cylinders at high altitude, was perhaps the most difficult. British craftsmen assembled superchargers by hand, testing each unit, adjusting clearances until performance matched specifications. American mass production demanded that every supercharger be identical, interchangeable, installable without adjustment. The engineering required was extraordinary. Tolerances measured in 10,000ths, surfaces polished to mirror smoothness, components balanced to eliminate vibration at 20,000 RPM. Meanwhile, British resistance intensified. The Rolls-Royce liaisons, growing suspicious of Packard's slow progress toward actual production, demanded facility tours. They discovered machine tools being modified, fixtures built for components that didn't match blueprint specifications. Confrontations became daily events. Hives, the senior British engineer, grew coldly furious. "You're gambling with British lives," he said during one heated meeting. "Every hour you waste on unauthorized changes is an hour without engines. Pilots are dying because you think American cleverness exceeds British experience." Vincent remained calm, though the pressure showed in deepening lines around his eyes, trembling hands that only whiskey could steady. "Mr. Hives, we're not changing your engine. We're changing how it's built. The result will be identical." "Engineering is not philosophy," Hives snapped. "The method determines the result. Your machines cannot achieve what British craftsmen accomplish through skill." The fundamental disagreement wasn't technical. It was philosophical. Britain believed excellence came from individual mastery, craftsmen who understood their work intuitively. America believed excellence came from systems, processes so refined that any trained worker could produce perfect components. The weather turned bitter. Detroit's winter arrived early, cold winds howling through factory gaps where heated air escaped. Workers arriving for early shifts found frost on machinery, ice in lubricant reservoirs. The factory operated continuously, furnaces burning coal around the clock, but the cold penetrated everything. Engineers worked in overcoats, breath visible in the drafty laboratory. Outside, Britain endured the Blitz, London burning nightly, cities reduced to rubble, civilians sleeping in underground stations while bombs fell. News arrived weekly. Coventry destroyed, Liverpool docks ablaze, Rolls-Royce's Derby factory damaged by near-miss bombing. The pressure became unbearable. Every day without production meant British pilots flying worn engines, maintenance crews cannibalizing damaged aircraft, squadrons grounded because no replacements existed. By February 1941, the redesign was mathematically complete. Every British dimension had been converted. Every component had been re-engineered for American production. Tolerances had been specified to micro-inch precision. Thread standards had been converted. Materials had been substituted and tested. The theoretical work was finished. Now came the test that mattered, building an actual engine. If the design was flawed, if some critical British wisdom had been lost in translation, they would discover it now. The first prototype was scheduled for assembly in March. Vincent authorized triple shifts. The machine shop ran continuously, components emerging from grinders and lathes, inspectors measuring everything, rejecting parts that missed tolerances by micro-inches. The factory smelled of cutting oil and hot metal, sounds of grinding and hammering echoing off brick walls. Britain had said, "Don't change it." Packard had changed everything. Now they would discover if American confidence exceeded American competence. March 1941. Assembly Bay 7 had been cleared of all other work, designated for the prototype. Early morning light filtered through east-facing windows, illuminating the assembly stand where the first American Merlin would be built. The engineers gathered silently, faces drawn from months of sleepless nights, hands shaking slightly from exhaustion and caffeine. They'd done everything correctly in theory. Now theory would meet reality, the unforgiving physics of metal under stress, combustion under pressure, bearings spinning at speeds where microscopic imperfections became catastrophic failures. The crankshaft was installed first, lowered into the crankcase with ceremony usually reserved for religious ritual. It had been ground by automated machinery, not hand-polished by craftsmen. The bearing surfaces gleamed, measured to 0.0001-inch tolerance, tighter than British specifications because American machines could achieve what British craftsmen could only approximate. The connecting rods followed, attached with American SAE bolts instead of Whitworth threads. Each rod had been weighed, balanced within 1.5 grams, tighter than British hand selection. Pistons came next, aluminum castings from American alloys, compression rings fitted with springs calibrated to exact tension. By afternoon, the engine resembled a Merlin, 12 cylinders in V formation, supercharger mounted prominently, reduction gearbox connecting crankshaft to propeller shaft. But it wasn't a Merlin built by Rolls-Royce craftsmen in Derby. It was a Merlin built by American machines in Detroit. Every component was interchangeable. Any piston would fit any cylinder. Any rod would fit any crankshaft journal. British engines were individual creations. American engines were industrial products. The test schedule was brutal. First, a cold compression check to verify cylinder sealing. Then, initial start and idle test, 15 minutes at 1,000 RPM. If the engine survived, progressive power tests, 30 minutes at 2,000 RPM, 1 hour at 2,400 RPM, finally maximum power at 3,000 RPM, maintaining 60 inches of manifold pressure. The British observers, still skeptical but professionally courteous, took positions in the observation gallery. Hives stood with arms crossed, expression neutral, but Vincent noticed his hands gripping the railing tightly. The compression test passed. All 12 cylinders showed identical pressure, 138 psi, exactly matching specifications. But compression was easy. The real test was combustion, heat, vibration, the 1,000 forces that destroyed engines. At 3 p.m., the test cell operator pressed the electric starter. The Merlin's V12 configuration meant cylinders fired in sequence, a rolling thunder that shook the reinforced concrete floor. The engine caught immediately, settling into rough, idle, exhaust smoke, turning from blue to clear as oil burned off new surfaces. Engineers monitored instruments, oil pressure steady at 60 psi, coolant temperature climbing normally, no unusual vibration detected. 30 minutes later, they advanced throttle to 2,000 RPM. The Merlin's note changed from rough idle to smooth roar. The propeller reduction gearbox, completely redesigned for American manufacturing, showed no vibration beyond normal parameters. Oil consumption was minimal. Coolant temperature stabilized at 95 degrees Celsius, slightly cooler than British engines, because American coolant passages had been optimized using fluid dynamics calculations instead of trial and error. At 2,400 RPM, the supercharger engaged fully, compressing intake air, forcing additional mixture into cylinders. Power output reached 850 horsepower. Still no problems. The final test began at 4:45 p.m., full military power, the regime that destroyed inadequate engines. The operator advanced throttle to maximum, adjusted mixture to rich, watched manifold pressure climb to 60 inches. The Merlin screamed, a sound that wasn't mechanical but organic, like a living thing pushed to extremes. The test cell shook despite reinforcement. Engineers watched instruments with faces drained of color. If any component was inadequate, if tolerances were wrong, if materials were weak, if some critical British wisdom had been ignored, the engine would fail now. Pistons would seize, bearings would spin, connecting rods would break, punching through crankcase walls with shrapnel violence. 1 hour passed. The engine maintained maximum power without variation. Oil pressure remained steady. Temperature stabilized. Vibration stayed within limits. The American Merlin, built from redesigned components by automated machinery, was producing 150 horsepower, 20 horsepower, more than British specifications. At 6 p.m., the operator retarded throttle, bringing the engine back to idle, then shut it down. In the sudden silence, engineers stared at each other in disbelief. It worked. Everything they'd done, every conversion, every redesign, every midnight calculation, had worked. Hives descended from the observation gallery slowly, face unreadable. He approached the engine, still radiating heat, metal ticking as it cooled. He touched the supercharger housing gently, almost reverently. "Gentlemen," he said quietly, "I owe you an apology. I believed American methods couldn't match British craftsmanship." He paused, choosing words carefully. "I was wrong. You haven't copied the Merlin. You've perfected it." The admission cost him pride, but honesty cost more. "How quickly can you produce them?" Vincent smiled for the first time in months. "We'll have 300 engines monthly by July, 600 by September, 1,000 by year's end." Numbers that would have been impossible using British methods. Numbers that would change the war. June 1944. Over Normandy's beaches, 3,000 Allied aircraft controlled the skies. Spitfires, Mustangs, Lancasters, every one powered by Packard Merlins. The engines that Britain said couldn't be changed, that American engineers rebuilt from scratch, now filled the air with thunder. By war's end, Packard had produced 55,523 Merlin engines, more than Rolls-Royce's total wartime production. The American engines were identical to British standards, but interchangeable, serviceable, rebuildable. A mechanic in North Africa could install a Detroit-built engine in a British Spitfire without modification. Mass production had matched craftsmanship, then exceeded it. The impact extended beyond simple numbers. Packard's redesign proved something revolutionary about industrial warfare, that democratic manufacturing, standardized, systematized, teachable to ordinary workers, could outproduce aristocratic craftsmanship. British engines were magnificent individual creations. American engines were magnificent because any factory could build them. By 1943, Packard was licensing their manufacturing techniques to British factories, teaching Rolls-Royce engineers the methods they'd once rejected. The Derby Works adopted decimal measurements. Hand-fitting gave way to automated grinding. Craftsmen became production workers, and output tripled. The long-term consequences transformed aviation manufacturing permanently. After the war, every jet engine, every turbine, every complex aerospace component was designed using Packard's principles. Tight tolerances achieved through machinery, components engineered for interchangeability, processes documented so thoroughly that any qualified manufacturer could reproduce them. The romantic era of craftsman-built engines ended. The modern era of precision mass production began. Not because American methods were inherently superior, but because war demanded quantities that craftsmanship couldn't achieve. The engineers returned to different lives. Vincent retired in 1945, decorated by both American and British governments, though he rarely spoke of the war. He'd proven his point, that necessity creates innovation, that desperation breeds excellence, that sometimes breaking the rules saves civilization. Others continued in aviation, designing jet engines, rockets, eventually spacecraft propulsion. A few struggled with peacetime, finding civilian engineering mundane after building machines that changed history. Robertson, the Scottish production chief, returned to Britain briefly, consulting for Rolls-Royce on their post-war manufacturing modernization. The irony amused him, teaching British engineers to build like Americans. Hives, the Rolls-Royce representative who'd initially opposed every American modification, became Packard's strongest advocate. After watching American production reach scales unimaginable in British factories, he wrote extensive reports recommending manufacturing reform. His recommendations were initially controversial. British engineering tradition resisted change, but combat results spoke undeniably. By 1943, RAF squadrons preferred Packard Merlins because spare parts were readily available, overhauls were faster, and replacement engines could be installed without squadron modification. Practicality overcame pride. The human cost of the delays was never officially calculated, but engineers did their own mathematics. If Packard had followed British specifications, first engines would have reached squadrons in mid-1942 instead of late 1941. 8 months of reduced production. Approximately 2,400 fewer engines. In 1941-42, when Britain was desperately short of fighters, Those missing engines might have meant squadrons grounded, convoys unprotected, bombers unable to strike German industry. How many pilots died flying worn engines that should have been replaced? How many missions failed because aircraft were grounded awaiting engines? The numbers were unknowable, but not unimaginable. The Packard Merlin became symbol of something larger than engineering, the vindication of democratic principles in industrial form. British society was hierarchical. Craftsmen served apprenticeships, learned trades from masters, maintained traditional standards. American society was egalitarian. Workers learned standardized procedures, operated machines, produced identical components. Britain believed excellence came from individual mastery. America believed excellence came from systematic organization. The war proved both correct, but in industrial warfare, American methods produced more, faster, cheaper. Decades later, historians rediscovered the story through declassified documents and aging engineer interviews. The redesign, once secret to avoid diplomatic complications, became recognized as critical to Allied victory. Academic papers analyzed the technical achievement, how dimensional conversions were calculated, how tolerances were determined, how materials were substituted. But the deeper lesson was philosophical, that sometimes progress requires abandoning tradition, that respect for expertise must balance against practical necessity, that being told, "Don't change it," sometimes means, "Please change it. We just can't admit we need your help." The last Packard Merlin rolled off the Detroit production line in September 1945, 6 days after Japan surrendered. Total production, 523 engines. Total flight hours, approximately 125 million. Total horsepower delivered, 64 billion. The numbers were staggering, but statistics couldn't capture the human reality. Pilots who survived because engines didn't fail, bombers that reached targets because power remained reliable, fighters that controlled skies because quantities overwhelmed opposition. The engine Britain said couldn't be changed had been changed completely, then proven right by the only measure that mattered: victory. The engineers who rebuilt the Merlin proved that when the stakes are high enough, innovation finds a way, even when told not to change a thing. Their story reminds us that progress often requires challenging established wisdom, that respect and rebellion can coexist, and that sometimes the best way to honor tradition is to improve upon it. If stories like this fascinate you, tales of engineering courage, wartime innovation, and the unsung heroes who changed history, subscribe to this channel. Share your thoughts in the comments. Would you have followed the rules, or would you have done what Packard did? History is filled with moments when someone decided the old way wasn't good enough. Let's explore them together.